semester, and it may last long. So I'll give two tutorials on soil mechanics. One is for the answers for our homeworks, in particular for those difficult questions. And the other tutorial is for, how to say, practice of our examinations. So the second tutorial gives us some, how to say, similar questions in examination paper. So I hope that you focus on those two tutorials and it will help you a lot in the examination. So let's see the first one, that is assignments or the homeworks, the answers for the homeworks in each chapters. Let's just go review of the soil mechanics we learned in this semester. So at the very beginning, what we learned the development of soil mechanics, right? The history of the soil mechanics. Actually, it is a very, very basic introduction about soil mechanics. And then the main part is start from the second chapter. The second chapter, what we learned. I hope you were all here, but nobody answered me the question. So, okay, let's say the second, in the second chapter, we learned the origin of soil, right? Origin of soil, how soil comes from. But in the second chapter, the main thing is about what? It's about the particle size distribution, right? The mechanical analysis, right? So we learned the particle size distribution curve, how we got the particle size distribution curve, and how we calculate CC and CU of a soil, and what is CU and CC? CU is the uniformity coefficient, CC is consistency coefficient, right? So if we know these two parameters, then based on these two parameters, we can judge if a soil is well distributed soil or a poly distributed soil, right? So if it is a well-graded or polygraded, right? And we know that there is a range for CC and CU. If CC is within 1, 2, 3 and CU is higher than 6, then the soil is well-graded. If not, it is a polygraded, right? This is the main thing about in chapter 2. And we know that soil is origin from what? From rock, right? It is just a circulation. Remember the photo we put in here, it is a circulation, a very big circulation. But it takes a very long time, okay? So this is what we learned in chapter 2. In chapter 3, actually, we talked about the weight and volume relationships. Just follow me, try to remember, right? So weight and volume relationship. We learned about some, we learned the definition of water content, saturation degree, dry unit weight, and unit weight, and those relationship between those parameters, right? We say that soil is a very special material because it is, it have 3 phases. One is water, air, and soil particle, right? That we say it is solid, right? We have solid part, liquid part, but liquid part consists of 2. One is water, another is air, right? So this causes a new parameter, some new parameters like void ratio definition, right? And saturation degree, right? Void ratio is a volume relationship. It is the void's volume divided the solid's volume, right? how we define void ratio. This is the definition of void ratio, right? And we have a porosity N, right? There is a relationship between void ratio and porosity. And what is saturation degree? Saturation degree is actually a weight relationship. It is the ratio between the weight of water and the solid's weight, right? Try to remember, right? It is the ratio between weight of water and weight of solids. So this is this is water content. Degree of saturation is that how much of the water volume to all of the volume of voids, right? That is saturation degree. And density. Density, we say that we have normal density or natural density. That is the weight divided the volume of the soil. And also we have dry density. Dry density is that actually the density that we exclude water. Only account the weight of the solids, right? So it is actually the weight of the solids divided the volume, right, of the soil. We give a very big table and this table lists how to calculate unit weight, dry unit weight, void ratio, saturation degree, porosity, and maybe other parameters like saturation unit weight, saturated unit weight, right? How to translate, how to got those parameters from other known parameters, right? This is what we learn in chapter 3, weight to volume relationship. And then we go to chapter 4. What do we learn in chapter 4? What do we learn in chapter 4? Actually, we learned the weight to volume relationship. Weight to volume relationship is basic. We learn some basic parameters of soil, and then we will learn some very special parameters of soil, like liquid limit, plastic limit, shrinkage limit, right? So we learn some limits in chapter 4. Let's open this. Open our textbook. It may help you to review. Fine. Let's go to here. Okay. Okay, in chapter 4, we learned actually the plasticity and structure of soil. The important thing we learned in this chapter is actually the limits of soil. Plastic limit, liquid limit, and shrinkage limit. And we learned how we obtain those limits in laboratory, right? We learned for plastic limit. For liquid limit, actually, we use a percussion cup or a four-cone method, right? And plastic limit, we use the crumble of the soil, how to say it? Soil rock, right? And plastic index. Plastic index is a difference between liquid limit and plastic limit, right? Plastic index PL equals to LL minus PL, right? Keep in mind the LL is always higher than plastic limit. And the shrinkage limit, we didn't go to very detail of shrinkage limits. We use, how to say, dry method in laboratory to get shrinkage limit. And we learned the liquidity index, consist index, that is the curve we got in laboratory for liquid limit and for liquid limit, right? The slope of the curve, we call it is liquidity index and consistency index. And later we learned something on soil structure, right? We say structure is very close relate to the plasticity of soil, right? This is what we learned in chapter 4, the limits of soil. And then in chapter 5, we learned the classification of soil. We learned two main methods. One is texture classification. Another is classification by engineering behavior. In this, we learned another two methods. One is AESHTO classification system. Another is unified soil classification system. And we say that this is much easier, actually much simpler than unified soil classification system. And what is texture classification system? Remember that the big triangle photo, right? The big triangle photo. One side is silt, one side, another side, the second side is clay, and the third side is what? It's for sand, right? And how to use the texture classification system to define a name to the soil. Just try to remember. And this two, another two methods is based on the liquid limits and the particle size, some limits, liquid limits and plastic index, as well as particle size distribution of soil to do the classification, right? Remember those big tables. In AESTO system, we actually classify into 7, right? Into 7 different types. If you can't remember, just go back to the textbook, try to find the table and go review again. This is the classification of soil in chapter 5. And in chapter 6, we learned the compaction of soil. Compaction of soil is a very important behavior of soil. The important thing we learned in here is a standard property test. Standard property test in here is to obtain the compaction curve, right? We say how to conduct a standard property test is that you make soil into different water content and do the compaction test, and you got 4 or 5 points distributes two sides of the optimum state, right? And then you got the curve. The peak point is the optimum state of the soil, defines the optimum water content and maximum dry density, right? And compared with standard property test, then it is modified property test. The modified property test is just enhance or we improve the input energy compared to standard property test. And then we learn some empirical relationship for compaction. And then field compaction, we introduced some machines to do the compaction in field. And then maybe some specification for field compaction and determination, field unit weight of compaction, right? And how to evaluation of soil as a compaction material, if it is good or not for compaction or not. And maybe later we explain some special compaction techniques, dynamic compaction, remember? This is about chapter 6. And then chapter 7, start from chapter 7, we said, then actually we start talking about mechanical properties of soil. Actually, compaction is somewhat a mechanical property of soil, but also it is something like very basic properties. And permeability is the first mechanical properties learned in soil. In this chapter, we learned what is permeability, right? And we gave a new concept, hydraulic conductivity. Hydraulic conductivity is used to describe the permeability of the soil. And then we learned how we got to the hydraulic conductivity. we have constant height test and another one is what? Constant height test and falling height test, right? In laboratory. Those two tests are all related to the size of the specimen, and we have actually equations for those two specimen, for those two methods to calculate mobility of the soil, right? And then we learned some methods to conduct a field mobility test, right? This is mobility. And then we learned a little bit about seepage. After we learned the mobility, we learned the fluid net uplift pressure under a hydraulic structure and a fluid net. We didn't go very detailed into seepage. We first jump to in situ stress and then go back to learn fluid net and uplift pressure, right? Let's see in situ stress. We said that we learn in situ stress because if you want to calculate sediment or shear stress of a soil, first you need to know the overburden stress is what, right? How much of the overburden stress. Then we need to calculate the in situ stress and maybe later how much load you applied to the soil, right? The total stress, okay? So the in situ stress, we learned 3 different situations. And the first is the most simplest one, stress in saturated soil without seepage. We said that the stress applied to a soil is the total stress, is the overburden stress upon the soil. If the soil is merged by water, you need to calculate the weight of the soil and also the weight of the water to the soil, right? And then stress in saturated soil with upward seepage. If there is upward seepage, remember the photo we showed in here. If we open the valve, there is upward seepage, right? It will reduce our effective stress, right? Because it is give an uplift to the soil, right? Actually reduce the weight of the soil. And then stress in a saturated soil with a downward seepage on the opposite, actually it is enhance the weight of the soil. And then after we learn these 3 situations, we defined a seepage force, right? Seepage force, we say it is a volume force, and it equals to the hydraulic gradient multiplied the weight of water unit weight, right? And we learn some special situation that is heavy in the soil, right? And then some dangerous situation that is a factor of safety against heavy. We say that if the effective stress equals to 0, that is the uplifted force and the weight of the soil is keep a balance equal, right? The soil have a tendency to be uplifted. So based on this, we can actually compare by effective stress and per water pressure to calculate the factor of safety, right? And then we learn the effective stress in a partial saturated soil. It is not very important. And in this chapter, we talk about fluid net a little bit. And then stress in a soil mass. This chapter is not very important. We won't have any questions on the examination paper about this chapter. Oh, no, we have. Remember that we learned the major stress, minor stress, right? In this chapter, you need to remember. You need to go through that. How to say? That part to learn those 2 very big equations to calculate sigma 1 and sigma 3. Okay, but I will give you the equations on the examination paper. And then it is compressibility of soil. That is a very big chapter, and this is the last part we learn in soil mechanics. It is a very important properties of soil, compressibility. We introduced the segment of our soil, right? It consists of 3 parts. The first part is elastic sediment, and then it is primary consolidation sediment, and then secondary consolidation sediment, right? You remember the inverse S shape of the sediment and time relationship. And then the main thing in here is the fundamentals of consolidation. What is consolidation, right? Remember that we explained the consolidation with what? With a spring cylinder model, right? In here. The spring cylinder model helps us to understand the consolidation process. Actually, it is a transition between effective stress and water pressure. But the total pressure is keep constant during consolidation, right? We say during consolidation, because squeeze out water, soil was shrink because squeeze out of water, right? And then we learned how we learn the consolidation of soil. We use one-dimension laboratory consolidation test. We use this consolidation test, and we explained the process of the consolidation test. And the main thing in here is a water ratio pressure plots. That is the results we can obtain from a consolidation test. How to got these plots? And after we got these plots, and we need to define the pre-consolidation pressure, right? And the slope of the curve. That is compressibility index of the curve. We say that this curve have 2 parts. One is flat and another is steep. The slope of these 2 parts gives us the swelling index and compressibility index. And the tipping point, the corresponding pressure of the tipping point actually gives us a pre-consolidation pressure. And later we explained how to calculate the sediment for the one-dimension primary consolidation. Use the water ratio pressure plot. Actually, we need to use CC right in here. But if the applied pressure is crossed the pre-consolidation pressure, we need to also consider the flatter part, right? In here we actually introduced actually two important equations to calculate sediment, right? And later we explained what is secondary consolidation and what is secondary consolidation sediment and how to calculate. We define a secondary consolidation coefficient C alpha, remember? And how to use C alpha to calculate the secondary consolidation sediment. We introduced that. And later, all the others, we didn't talk about that. Okay, this is the main thing in soil mechanics we learned this semester. I hope after I go review of all those chapters, then you can remind yourself what we learned in soil mechanics. Have a whole structure in your mind. Okay. Then let's see the homework first.